Okay, so it's sort of a wrap-up class, wrap-up lecture to conclude the course and to give it more of an outlook and to contextualize what we've learned in the course thus far. So during the course, what we've learned, we spoke about a number of high-level topics. The first being distributed systems, which kind of we split into two. We had some initial courses on RMI and concepts of distributed systems, and then later in the course we introduced some additional concepts relating to consensus and so forth. Later on in the course, in the second kind of segment, we spoke about processing large amounts of unstructured information, text, data, whatever it might be, using some of these frameworks and concepts, key amongst which are MapReduce Hadoop, HDFS, PIG, Spark, and so forth. Also, we could add in there Kafka, which I guess is not in the tag cloud. We spoke then about indexing and retrieval over larger collections of text documents, how to build inverted indexes, how ranking works to be able to prioritize information of most likelihood to be relevant to the user using TF-IDF, PageRank, and so forth. And in the final kind of segment of the course, we spoke about storing and managing and querying semi-structured information, such as simple key value stores, JSON documents, graph databases, and so forth. So we spoke about the concepts of NoSQL systems, distributed databases, and so forth. So that kind of brings us full circle on the course. At the very start of the course, in the very first lecture, we spoke about the value of data, and we spoke about this anecdote about how John Snow used data to identify the cause or a vector of infection for cholera in London in 1854, I think it was. And we also spoke about Twitter in the very first class, and we spoke a little bit, okay, so it's the architecture from 2013, but we spoke about how we would see these elements in the course. So we spoke a lot about Hadoop. Okay, we didn't speak about mobile applications. We spoke about NoSQL stores. Redis is a key value store, in-memory key value store used for caching data. And we spoke about inverted indexes and Lucene and Elasticsearch. Essentially here, Earlybird is a Lucene clone. It's built on Lucene, so it's a similar system, let's say, to Elasticsearch. So we have seen these sort of three different elements with respect to processing large amounts of data, managing and querying large amounts of data, and indexing and storing text over multiple machines. We also spoke quite a bit about information retrieval in terms of Google, how Google works. We spoke, about elements of crawling, how text documents can be indexed, what sorts of ranking systems can be used, and so forth. So we spoke quite a bit about also kind of web search architectures and techniques, information retrieval techniques. Sort of an introduction to the main concepts that are involved there. So in general, these sorts of techniques are widely used in many companies, particularly companies that deal with data on the web. Companies and organizations, right? So there are also nonprofit organizations like Wikimedia, managing Wikipedia, Wikidata, and so forth that use these sorts of techniques that we've seen to manage, query, and process very large amounts of information. So in terms of the kind of overall concepts we've seen, hopefully with the labs, you've gotten some hands-on experience with working with large data sets. So we've not worked with the super large data sets in the labs, admittedly, but that's more for a practical issue and to reduce, the processing time. But you have worked with data sets where it's not possible to kind of by brute force keep programming and try changing things, right? So, we've seen the principles of working with small examples, testing and making sure that the script is okay before running it on the large data set to avoid losing time. And also to be able to ensure that we can always see the progress of the task, if it's progressing or not, which is offered by default by frameworks like MapReduce and Spark. So hopefully you have a little bit of experience now working with large data sets and understand some of the practical issues and difficulties and challenges of that. Also with the projects, you will probably encounter similar challenges. We spoke a lot about distribution and the importance of being able to scale over multiple machines rather than trying to scale within one machine. The idea of being able to add machines to be able to scale more flexibly and more economically. We also spoke about the challenges in terms of having to think about individual machines going offline, how to have fault tolerance, the importance of replication. But when we have replication, what happens if machines differ in terms of the values they return, how to establish consensus, the CAP theorem, and so forth. So you should have a general idea of some of the values, the value, but also the challenges of distribution in terms of avoiding bottlenecks and so forth. So in terms of concrete frameworks, we've spoken about Hadoop, Pig, Giraffe, Spark. Also, should add here Kafka. Also for distributed storage, we spoke about different types of NoSQL systems. And the systems that we spoke about were sort of selectively chosen to give you an instance of each of the main types of NoSQL systems. So for example, HBase is very similar to Cassandra, and Cassandra is generally more popular now. So CouchDB is a document database, a bit like Elasticsearch and MongoDB and so forth. So you've gotten a sort of a flavor and a taste, and you should be, you should understand if you work in a company or you go to work for a company that uses HBase, I think you won't have much difficulty translating what you've learned from this course and applying it to the HBase case, for example. So any questions or doubts? Okay, so with respect to the overall sort of area of big data and the courses that you've seen, data-related courses you've seen, maybe in the faculty in the CCE or in other departments, it's kind of worthwhile reflecting on the careers and what skills are most important, most valued for jobs and so forth, or what are most valued as well if you want to pursue a master's, a PhD, or to continue in research in the area as well. So somehow the two are kind of maybe related, but this focuses mainly on job postings. So there's a lot of hype around data science that's been, growing over time, over the past decade, let's say. So we can kind of dive a little bit into that topic and see what kinds of skills are important if you want to pursue a career in data science, which is quite a broad term, but we can break it down further. So first thing to note is that there is a high demand for data science, data scientists, people with skills to be data scientists in the job market. So the shortage of data scientists is sort of a known problem, that there's a lot of demand for people with skills in data. What sorts of skills do you need to be a data scientist? Well, I've been collecting each year some analyses. There are blog posts and there are questions on Quora and people give an opinionated response, but I kind of prefer these more analytical studies that try to extract skills like keywords from job postings. It seems to be quite concrete. So it is a little bit flawed, which I'll mention in a second, but it's somehow more objective, I think, to get an idea of what percentages of job postings, job offers mention the skill. It's quite a simple analysis, but somehow more objective than some of the other discussions I've seen. So focusing on these types of analyses, we see the top 10 in-demand skills for data scientists, where we see SQL is the top. 56% of job postings for data scientists mention SQL. We see Hadoop, Python, Java, or Hive, MapReduce, NoSQL, Pig, and SAS. So SQL you would have seen in the database course. It's a requisite of taking this course, I believe, if I remember correctly. Hadoop, we've seen in this course, we've spoken about at length. Python is often used not in terms of big data, but in terms of data analysis or data machine learning type aspects relating to data science. Java is more useful for what we would call data engineering. I'll talk about this a little bit later, but the sorts of things we saw in this course. Or you probably have already seen, or in another course, Hive, MapReduce, NoSQL, Pig, SAS. So we see we've covered here some useful topics or some useful skills, including here Hadoop, Java. We've worked with Java quite a bit. Hive we've not seen, but we've seen Pig, which is quite similar. MapReduce, NoSQL systems we've spoken about at length. What is SAS? SAS is effectively software. It's statistical analysis system or software, something like that. It's a statistical analysis system. It's somehow a commercial version of something like or maybe something like I forgot the name. MATLAB. These sorts of languages, but it's rather than a language, it's a sort of a system that will help you process statistics. Any questions or doubts? Okay, and if you want to see more, I've left the links in this comes from the source here. 2017, not to go into too much detail, but we can see some similar, familiar things here again. Python, this is or SQL, Hadoop, Java, SAS, Spark. Spark we see it wasn't in 2016, it appears in 2017. It's a different analysis, different data, and so forth. But Spark, MATLAB, Hive, Tableau. Tableau is a data visualization software, I guess. I've never used Tableau, but it's useful for data visualization. So again, we see some relevant concepts that we've, Hadoop and Spark, Java. Hive again would rather be Pig we saw, but we've seen some of these concepts in this course. 2018, not to delve into too much detail again, Python, SQL, or Java, Hadoop, SAS, Spark, C, machine learning. Some machine learning stuff is implemented in C, although Python, of course, is quite popular. Scala, NoSQL, Tableau, MATLAB, Hive, Excel, Cassandra, MapReduce, TensorFlow, Pig. Again, we see some concepts that we've covered. So just to mention, one of the limitations of this sort of keyword-based approach to the analysis of job postings is, of course, that Cassandra is an NoSQL system, and Hadoop could be split with something like MapReduce. You see these sort of synonyms here, or almost synonyms, right? Hadoop is an open source implementation of the MapReduce framework, but there is actually these synonyms in this context in NoSQL. Here we see Cassandra, so there's a tendency that things can be split. It's not so easy just to take the keywords, but as a rough analysis, I think again it's useful to see what's popular. 2019, some familiar things again: Python, or SQL, Spark, Hadoop, Java, Tableau, AWS, which is Amazon Web Services, which we've not seen in the course, but you would be better prepared to take on Amazon Web Services about managing clusters of machines and being able to run jobs in Spark or Hadoop on them. SAS, Hive, TensorFlow for learning, Scala, C++, Excel, Azure, Microsoft Azure, which is essentially the Microsoft's answer to AWS. And 2020, so Python, Excel, SQL, Spark, AWS, Scala, or Java, Tableau, Hadoop, SAS, and so forth.
Prof,
Yep.
Prof, a question. When in a job description say that they're looking for a data scientist, they assume that the the person who is applying should know machine learning.
Actually, I'll answer that on the next slide, or if I don't, you can ask me again. But I'll come to that. Yeah.
Thanks. Okay.
Okay. Yeah. So we see some familiar concepts. What things might you know? I guess you know Scala. Okay, we actually spoke about that. It's used also for Spark. SAS, we spoke about TensorFlow, machine learning. MATLAB, you probably know of. Azure, yeah, we spoke about PyTorch, machine learning, deep learning. Perl, Perl programming language. Keras is deep learning library API for Python. C Sharp. SPSS is statistical package, something. It's IBM statistical analysis, sort of business analytics sort of software. Ruby, programming language. C, programming language. GCP, it's probably no, yeah, it's Google Cloud Platform, Google Cloud effectively, and Go, another programming language by Google, that's gaining popularity a little bit. So yeah, we see, you know, again, taking this course, you picked up things like Spark, AWS, even though you haven't seen it. When you do see it, I think a lot of things will be familiar from using the cluster. The reason why we don't use AWS, or we don't really get into those topics, AWS, GCP, is that they're just commercial. I don't like, you know, there's AWS, there's Azure, and there's Google Cloud Platform. They're kind of commercial things. I don't really like marketing or teaching you one particular platform, you know, so we try to stick with open source stuff. But a lot of things will be familiar if you start to use these sorts of services. Yeah, so we see some things that you would have, you know, you would have learned in the course, so you can match some more of those keywords. So with respect to what overall data scientist has been this sort of umbrella term, but really there's sort of three different kinds of job titles that have kind of been identified, and you can sort of see a difference if you do clustering on the different types of skills that are required. So there's the concept of data engineer, data scientist, and data analyst. So data engineer kind of intuitively refers to this concept of preparing the data, managing the data, taking the massive amounts of data and then producing a small CSV that could be useful. So it's this sort of like taking the raw data, massaging it, managing it, being able to query it, process it, and so forth. Data scientists refers more so to people who take maybe a reduced set of data, maybe a CSV file, and then start to apply machine learning techniques, clustering, you know, using it to train deep learning models. This sort of more like, let's say, learning type processes on data in order to build models, to make predictions, to provide classifications, to identify clusters, and so forth. Analyst is a little bit more towards the business side. So essentially an analyst might not require such, so data scientists as well, sorry, I should mention also the statistical elements, the statistical processing of the data, hypothesis testing, you know, correlations, extracting this sort of information. Analyst is a little bit more in terms of, you know, they still require programming skills and so forth, but they're mainly going to be analyzing the data to be able to, they're somehow between the data world and the business world. So they might be more into visualizing, into analyzing visualizations, into interpreting statistics and so forth. So it kind of goes often in this direction from engineer to data scientist to analyst, but you can have people who are proficient in 3, who are proficient in 2, who are only proficient in 1. You know, it's sort of, I would consider it as a very rough analogy, engineer to be sort of back-end data, and data scientist and analyst to be kind of front-end data / user, you know. It's a very loose analogy. Anyways, what's interesting here is that in this report, they have looked at the skills for the different kind of categories of data science. And we see that this course is very much focused on data engineer, which based on my description probably doesn't make so much, it's not so surprising, right? So we see Spark is super important for data engineering. Which is maybe no surprise. AWS is more important. Python is still important here, right? But we can see it's much more important for a data scientist. Relatively speaking, Java is more important for an engineer than for the other for the analyst or the data scientist. So we see analysts are working more with Excel or SQL to be able to run queries, extract data, analyze data in spreadsheets, and also in Tableau, which is used for visualization. So yeah, so we see that the topics of this course are really most relevant for the data engineering side of things. But I think, even if you're really interested in the machine learning aspect, having at least one course on like Spark, AWS, Scala, I think it's important just to be able to understand, if you're working with data engineers, to be able to converse about, the process of getting the CSV or whatever that's used for training the models. I think it's certainly useful. Yeah. So hopefully that answers the question. Jose, was it? I think you asked.
Yes.
Yeah. Okay.
Yes.
Any questions or comments on this?
Just to comment that catch my attention that in the list appear the solutions, the cloud computing solution from Google, the Microsoft, and Amazon, but IBM is missing.
I don't even know what IBM's service is called. What's IBM's
Cloud service?
What's it called?
IBM Cloud Services. IBM Cloud Services.
Cloud services. Okay. Yeah. I haven't much experience. I don't know relatively how popular they are, but I have seen in these sorts of analyses that Amazon Web Services appears to be the most popular. It is sort of the model. It's been copied to a certain extent by Google Cloud and by Azure, for example. I don't know why AWS in particular is so popular. I would imagine that all of these services provide similar sorts of services for similar-ish prices, I would imagine. I don't really know. In terms of the IBM offering as well, I don't really know too much. But what I have seen is AWS is the most popular, but it's also the longest established service of this type, let's say. And also just to mention that a lot of these services, if you wanted to play with them, they offer free credits. So you can go in there, you can get some credits for free, and you can start to process data. It's also possible. Yep. Any other questions or doubts? Okay, so I think in general, one criticism of the course has been it's not really clear why all of these topics, but I've been trying to keep in the course some of the more relevant topics that you would see in practice. I also cover some things not mentioned here that I think are important, such as the information retrieval aspects. And so, we see useful things for data science, for data engineering, and so forth. So it's sort of, I know it's a mix of all these different skills and different topics every week, but if you've picked up on these topics, you have some nice keywords for your CV at least. So there's so many systems and there's so many different frameworks and NoSQL systems and the whole area is saturated with all these different solutions that kind of copy each other, or they have one particular feature that does better than the other. But I think aside from the systems and the languages, I hope as well, that you learn more about the raw ingredients, the things like the replication, distribution, how things are partitioned, consistent hashing, in terms of sorts, in terms of sequential access on disk, never avoiding lots of random access. because these ingredients are most important, because you can package these ingredients up into a recipe for a new system, and maybe in 10 years all of the systems will be redundant that we speak about now, and there'll be all these new systems. But I think these essential ingredients, or the technical elements of these systems and these frameworks, is important to understand the values and costs of distribution, the things to avoid, too much use of the network, being fault tolerant, how to gain consensus in a network. These sorts of ingredients are what I think are valuable in order to be able to adapt to new systems that you'll see in practice, or that will start to emerge, continue to emerge in the next years. Although I would say that the systems are starting to converge a bit, in the sense that it's been around a while, this area. And Spark is establishing itself as the kind of lead runner over, let's say, Hadoop, and Cassandra is winning over HBase, and there's sort of established systems emerging now. But the ingredients are important, rather than the recipe, the final systems. Yeah, so I think one of the big challenges as well for big data in general is this idea of having a problem, and knowing what you should apply to it. So half of the battle is choosing the right framework, the right system, the right database system. And this is not trivial. This is something that takes experience, it takes knowledge. But I think in general, from this course, you should start to already be able to distinguish different types of problems and different types of systems and what they might be useful for. Also, there's a lot of money, for example, in big data consultancy. So if you wanted to do consultancy, or you just wanted to know this stuff just to be ready for your master's, your PhD, your job, well, maybe if you want to be a consultant, if you like the smell of money, for example, we could have a look and see at the sorts of things that we would have to be able to decide as a big data consultant. So I'll give you some typical kind of scenarios, and we'll see how we get on in terms of figuring out what sort of technology to use, right? So I've crawled 30 million job postings, and I want to perform a word count. What should I use? So I want to analyze, I want to see SQL versus Hadoop versus Spark versus, in these job postings. So the first one is kind of a trick question, right? So we don't need to use anything fancy here. If you're thinking, okay, we could use Hadoop, we did a word count in Hadoop, or we saw how to do that. We could do that as well, that would be fine, or we could also use Spark. So just because we're counting simple words, we could just count the words in memory on one machine. That shouldn't be a problem. There's few unique words. So local machine in memory is a good option, or otherwise we could think about Spark. Maybe in memory RDDs would be a good choice. It would be slower and MapReduce because we have to use the disk, and we don't really need to use the disk because the data we're managing is just words. So we might encounter maybe 300,000 unique words that we need to keep counts for. So it should be okay in memory. My website has 120 million users. Each user has personal profile data, photos, and friends. I have 12 machines available. What should I use? So specifically what we need is, we have a website and the users have their data. We already spoke about a similar scenario before. And what we'd like to do is manage the data such that we can retrieve it when the user loads their photos page, their friends page, or just loads their profile page. So what would we use? So would we use Hadoop, Spark, Kafka, relational database system, NoSQL, RMI? What would you suggest? seems like nobody likes money here. You don't want to be big data consultants. So we should use NoSQL, right? So essentially we have 12 machines available. We have probably a large amount of data, 120 million users. We're probably going to be talking about like billions of data values or data points, right? So probably we wouldn't like as well, maybe your website's going to grow. So we would like to have scale. So using a NoSQL store will allow us to scale over multiple machines to be able to have replication, fault tolerance, and so forth. So since we have a website, we could probably assume that the types of queries we're going to do are going to be quite static. It's like when the user reaches our web page and has like profile.php or profile whatever.html, we're going to be loading the same sort of data: their name, their image, their maybe some details about their friends. So the queries that we're going to be doing are very repetitive. So we can use maybe something like MapReduce or Spark to pre-process all of the data that we need and just package it so that essentially each key refers to the data we need for a web page, for example. And that way we can then do very efficient queries at large scale over the data that we need. So probably a NoSQL system like Cassandra, maybe even MongoDB if we are managing JSON data for our web application. My company has 30,000 employees, which is pretty good. We need to store and query info about bank accounts, insurance, and so forth. What should I use? Any ideas?
¿Esta pregunta es solo sobre cómo vamos a hacer como las consultas o también nos preocupamos como de qué forma se guardan los archivos, por ejemplo?
Yeah, so it's about both. It's about the queries and it's also about the way that the data are managed. So it's in general the whole thing, right? So you're kind of tasked with this system for managing and processing the queries in this case. Yeah. So there's
relational.
Yep, there's some suggestions in the chat, and yeah, exactly. You want SQL, you want ACID, you want relational databases here. You don't want, data to be, you want the guarantees, the safety of ACID, and the scale of your data. You have 30,000 employees. Obviously, you're going to have more than 30,000 data points, but you're not going to have that much. It's going to be something that Postgres should be able to manage quite comfortably, or whatever relational database system you want to use quite comfortably on a machine. So SQL, ACID, traditional relational databases, not probably a good idea to use MongoDB or to use NoSQL in this case. So yeah, so scale is not really an issue. Queries might be quite diverse. ACID, reliability is important. So relational database. Okay, my telescope is generating millions of images of the sky every night, but I'm only interested in finding some images that might indicate supernovae. What should I use? So you have to imagine that there's this new telescope, it's generating millions of images, video of the sky every night, and you want to extract from that. Yeah, so suggestions of Kafka. Yeah, so Kafka seems like a very good option because we have this dynamic data that we have coming in, and we might need to send it to certain, consumers that can then check if it might be a supernova, maybe produce that and write it back to another message stream that's consumed by some other consumer that will check it in more detail and so forth. So Kafka seems to be a good framework to use just in terms of, redirecting, processing, filtering dynamic data. So a streaming platform like Kafka, others are available, and Kafka is quite heavily used in the university. The people working on projects like Alerce are using Kafka for managing data from the telescopes in a decentralized setting as well. So different universities are receiving different information from different streams. Okay, so we're doing better in terms of the consultancy now. We're on a roll. I'm scraping data about video games and their characters from various wikis. In total, I've scraped information from about 1 million pages, and now I want to be able to search over what I have. For example, to find all non-human characters in a particular video game or platforming games featuring plumbers. What should I use? So when I talk about wikis, I'm talking about, you've probably seen these wikis, right? Something like Wikipedia, but for dedicated topics, where they have mostly text, but they also have, the sort of metadata in the top right corner that will give some details about some properties and attributes. If it's a video game, it might give publisher, Nintendo, year, first published, 2004, this sort of stuff. So we want to scrape this and index that content. So the scraping and the indexing, we could use something like Notch, a crawler for that. But what we're interested in here mainly is the data management system. So what kind of, would we use an SQL or relational database, for example, to index the content and do searches over it? Or maybe there's some other alternatives we could use. So what do you think? Let me see what time it is.
Could be something like the last one that we saw, the Neo4j.
Neo4j, yeah. So we could use a NoSQL system. So yeah. Neo4j would be a pretty good option. So that would allow us to navigate connections and so forth. I think one reason why Neo4j might not be so fitting here is that Neo4j is not great for documents. It's not great. And, I could imagine here in this scenario, we'll have a lot of text, like from the articles or from the paragraphs. So NoSQL in general is the right solution. In general, we need some sort of query language. It can't just be like Cassandra where we have keys and we get values, because obviously we are going to have, different types of searches and queries over the documents. It's not really clear what immediately right now. So if we have a lot of text, if that's part of it, then a document store seems to be a good option. So something like MongoDB, which will allow, or Elasticsearch, in particular, if we have a lot of, what's the key difference between MongoDB and Elasticsearch? They both allow for indexing JSON like documents, but Elasticsearch is really dedicated more to text. It uses Lucene and has a very good engine underneath for querying text. So these would be good options, but Neo4j would also be a good option, particularly if we have more, we want to, explore more the graph of how different characters are connected to different games and different publishers connected to, if we really like that graph abstraction, then a graph database could be a nice option. In this case, we avoid the need to define a relational schema by using a graph database, which is nice because initially we might not know what kinds of data the wiki is going to give us. So, it's sort of a more flexible option. Okay, so we can take a break for a little bit. We're just going to continue with a few more examples and then wrap up. So we'll take a break until 15:20. I don't think there's so much left in the class. But, any questions?
Profe, lo que habló como de consultorías, ¿qué tan importante cree, o sea, que se valore como la experiencia como para ser contratado en una consultora?
No tengo idea. I have no idea. So I know of people who got into consultancy. They had done like PhDs, I think. Some of them, I don't know. I don't think that's necessary at all to have that level of expertise. Those I spoke with, I mean, essentially there's a lot of training on the job as well. Essentially all this sort of technical background knowledge is super useful, of course, but there's a lot of training on the job for what kind of, the type of consultancy that you would be doing. So I really don't know. I don't know, what's the path towards that. A lot of the people I know who got into consultancy, they made a lot of money. They did PhDs beforehand, but I don't know if that's necessary. And I do believe that they said that really, like when talking with them, they said it wasn't really things they learned. I mean, there's a general technical knowledge that helps, but a lot of the stuff they just learn on the job. So I don't I don't have much more to say.
Okay, gracias.
Okay. Any other questions? Or? Okay. Adam?
Yeah, I have another question regarding projects. Should our projects be able to process some queries, or may the data be static and all our analysis be just based on static queries?
Yeah, so that's completely up to you. So there's no restriction on that. The most typical is to take a big bunch of data and do some analyses of that. So it's the kind of like the data engineering / science part. So it's like, you know, you take a big data set and you define some interesting kinds of questions you want to answer, and you answer them over the static data. There have been projects as well built on NoSQL stores, like indexing very large amounts of data and building a simple web application over you know, MongoDB or Cassandra. But that's completely your choice. So the main thing would be to use something from the course for applied to an interesting that involves lots of data and a problem that's interesting to you as a group.
Thank you.
Okay. Any other questions? Okay, let's take a break. So I'll stop the share. Pause record. Okay, so we can continue the next scenario. So we have maybe 3 or 4 more scenarios. I have descriptions of millions of patents, and I want to create a system to find the key patents relating to a given technology or application. So typically in patents, you'll have different sections. You know, you'll have the title, you'll have the authors, patent number, you'll have some claims, you'll have a lot of text description. So we can assume that we have documents with some fields, but heavy on text. So what would be a good choice in this sort of scenario? Elasticsearch would be good. So MapReduce we could use to pre-process the patents, but what we'd like here is to enable the search. Yeah. So something like Elasticsearch would be good, or Lucene directly, or Solr, because we'll have a lot of kind of keyword searches like oscillating bathtub or whatever. We'd like to find the relevant patents. Of course, it would also be great if we could detect the relevance or importance of patents. So we could use measures like TF-IDF, which Elasticsearch provides, or a variant of TF-IDF. We could also think about, since patents cite other patents, we could use, what algorithm could we use? So we have patents who cite other patents forming a graph, and we could consider using PageRank to identify the key patents that are being referenced. So we need keyword search with ranking mainly in this scenario, probably. So we can use inverted indexes as implemented in Lucene, Elasticsearch, Solr, maybe even MongoDB, for example. Relevance ranking, TF-IDF. Importance ranking, we could use PageRank to find the kind of most central or key patents. Although it must be said that PageRank in this case would have a bias towards older patents, because the longer a patent has been around, the more links or citations it would tend to receive from other patents. So we might need to be a little bit careful with that. But yeah. Given GPS billing info of mobile phones, weather updates, accident reports, time of day, historical data, and city maps, I want to plan the best routes from A to B. What should I use? So this is somewhat like the Waze application that you might be familiar with. Also, Google Maps provides some estimations of times and best routes. So route planning, what might be a good thing to use here, to a good framework to start with to build this? So the best routes from A to B, Neo4j is an interesting suggestion, because it would give us this sort of path finding, right? It would allow us to find connections from A to B, which might be useful. Yeah. So, but in general, the difficulty with Neo4j in this context would be the sort of dynamic aspect that we have all this sort of flood of data coming in, sort of like a streams of data, and that would make it challenging for Neo4j. But we might include Neo4j as we might have a connector to Neo4j, for example, for finding paths or for something to calculate paths in a graph. So Neo4j it could definitely be a component here, or some sort of graph database or graph analysis framework. However, given that our data are dynamic, we're probably going to need on a higher level, our data to come into something like Kafka, like a streaming platform. And that streaming platform can then redirect the different streams of dynamic data from different locations to the consumers, the producers, or the connectors, the databases that should be indexing the data. So Kafka to coordinate, and then we would need probably maybe some more specific, even also machine learning algorithms, for example, on the other ends, consuming and producing the data, filtering the data, making predictions, and so forth. So, but Kafka sounds like a good starting point for organizing such a data processing architecture, given that the data are dynamic. Okay. I have information about tens of millions of papers and millions of movies, and I want to compute the Erdős-Bacon numbers for all people. What should I use? So I guess you're familiar with the Erdős number or the Bacon number. So the Erdős number is, how close you are in the co-authorship graph with Erdős. So Erdős has 0. If you've co-authored directly with Erdős, a publication, he was famous for traveling around and working with people and working with lots of people and publishing lots of papers with diverse authors. Those people who co-authored directly with them have an Erdős number of 1. Those who co-authored with someone who has an Erdős number of 1, but they themselves do not have an Erdős number of 1, would have an Erdős number of 2, and so forth. So those of distance 2 away from Erdős would have a number 2, and so forth. Bacon number is the same idea, but it's co-starring in a movie with Kevin Bacon. So his co-stars would have a Bacon number of 1, Bacon number of 2, if they starred with someone who co-starred with Bacon, and so forth. Erdős-Bacon would be I believe the sum or the max, I don't remember which, but it would be some combination of both. I guess the sum, yeah, it would be the sum of the Erdős number and the Bacon number. So what would I use if I wanted to take a bunch of data and compute the Erdős-Bacon numbers for everyone? So a static collection of data and compute these Erdős-Bacon numbers. Okay, so the fact that it's sort of a static file or 2 files that we have and we want to batch process them, it kind of leans towards using something like Hadoop or Spark. Maybe Spark would be better because there's this sort of recursion in there. So maybe we could even get the data into an in-memory ORDD, for example, to help make the process more efficient. We could also consider using a dedicated graph processing framework, such as Giraffe, GraphX, the sort of thing like Giraffe that we use for the PageRank computation. So these in particular would probably be the best option, since what we have essentially is a graph connecting people that have co-authored with each other or connecting people who have co-starred in the same movie together. And we can apply this sort of recursive algorithms on using these frameworks. We shouldn't here, it might be tempting to say that we could use Neo4j, but because we want to compute the Erdős-Bacon numbers for millions of people, it's sort of like, in a relational database, we're often trying to process transactions, inserts, updates, deletes, queries that don't touch a large amount of the data. Typically, you're just accessing maybe a few blocks of the data on disk, a small fraction in general, many of these transactions, but we need to process lots of them. when we want to process the whole data or a large fraction of the data in sort of batch, we prefer something like MapReduce, Hadoop, Spark, something like that. So in a similar sense here, Neo4j is good for processing kind of these low-level transactions, but it's not great for doing this sort of batch-level processing over millions of people all at once. Because in general, it works with random accesses on the disk, which will, when we're doing millions of them, it's going to be very slow. So in general, for that reason, something like Giraffe or GraphX would be good, a distributed processing, a graph processing framework. I'm collecting information about research networks in Latin America. I have information about author affiliations, publications, topics, etc. Given a particular user, I want to recommend collaborators in the region based on the co-author network of that user. What should I use? So this is a similar sort of scenario where we have, these sorts of authors, publications, topics, and then based on the sort of network of co-authors and topics, we want to be able to recommend collaborators. So for that particular user. So what should we use in this case? So the one interesting thing here is that we're kind of doing this for a particular user now. It's like a user enters the system and they can get some recommendations. So we could possibly consider one of two approaches, right? So the first approach is that a graph database like Neo4j sounds like a good option because we can find paths between, we can sort of query based on paths. We can query the graph, query the network. We can represent directly the co-author network as a graph and do queries on that. There is maybe a second alternative, which is that we take our graph and we pre-process everything to compute all the recommendations statically. And then we index that in Cassandra or something like that. So we just say, okay, this user here, these are the recommendations for that. And we could update that cyclically, maybe once a month or something to update the recommendations if they don't change that frequently. But in general, it might be more comfortable to just use Neo4j for this and to do the queries online. So to find the paths for a particular user online, for example. The key difference is, again, that here we're kind of touching a smaller amount of the data because we're focused on a particular user each time. Okay. I'm working with a company that has a web application used by more than a gazillion users every second, a gazillion being a very large number. Sometimes new software is deployed that can have bugs, turning some users away. I want to monitor and search over logs for recurring errors that might be affecting our user experience. What should I use? And this sort of scenario of log analysis is very, very common in many sort of medium to large companies. That their web logs in particular produce so much data. There's so many requests that you can have millions of records every day being produced, or maybe even every hour. Excuse me, if you have a very busy website. So what should we use in this scenario? Excuse me. Yep. So Elasticsearch and Kibana. With the Logstash, there's this ELK framework, which is specifically designed for this sort of task. So Elasticsearch, Logstash and Kibana, this ELK framework is a very good choice. Depending also on the types of analysis that we'd like to do, we might consider the logs to be a stream of dynamic data, and to consider using something like Kafka, for example. Maybe we have Kafka that streams some data into Elasticsearch, streams other data into other consumers or producers. So we could think about something like a streaming platform like Kafka, maybe just to detect important events, maybe to filter down the stuff that we're indexing or that we're considering later. And then we could consider using distributed inverted indexes, maybe Elasticsearch, Solr, the ELK framework to index and search and aggregate over events. I think this is the last one. I'm working in a cinema. Given a large collection of movie data like IMDb, I want to compute profiles for people who work in movies. So I want to compute profiles for actors, directors, etc. including how many movies they've directed or starred in, what are the average ratings of the movies, their most frequent collaborators, awards won, and so forth. Afterwards, when a user visits the webpage, they can hover their mouse over any person to view that person's profile, like a summarized profile. So importantly, the details about the profile are kind of static, right? We just define them as part of the application. So what should I use for this? So what kind of framework, what kind of system should I use to power this or to enable this sort of functionality? So the first thing would be, there's two options here. The first option is that we load all of the data into a database with a query language like SQL, like maybe Neo4j, maybe even MongoDB. And then we query at runtime to do the aggregations, to find the average ratings of their movies, to find their most frequent collaborators, to find how many awards they've won, right? So at runtime, we query the data to find out this information. So this has the cost of having to evaluate more expensive queries at runtime. And the queries will be very repetitive if the profile is defined, assuming that the information that we include in the profile is relatively static and we don't change it that often. So it would probably make sense to pre-compute these profiles as maybe a JSON document, and we can maybe think about, storing them in MongoDB or Elasticsearch, or we might even consider maybe something like Cassandra. So if we have a lot of users visiting our webpage in particular, so we want to avoid expensive queries at runtime. So probably the best idea would be to aggregate or to pre-compute the profiles and then index the data in a simpler sort of way for querying. So maybe MapReduce or Spark to compute the profiles. And then maybe a NoSQL key value or document store like Cassandra or MongoDB to index the profiles. The disadvantage of this is that every week or whenever we want to update, we're going to have to recompute all the profile data again from scratch. I mean, we can do some updates on the fly, but we would have to manage that outside of the database. Okay, so hopefully that was what I explained there made some sense. These sorts of decisions are the kind of, something that can be difficult in these sort of big data projects, these projects involving large amounts of data. It can be important to choose the correct framework, the correct system, and it can save a lot of time and a lot of hassle to make a good choice in terms of what you're going to use for a particular data intensive project. So, hopefully with these sorts of scenarios and having seen what you've seen in the course, you can make an appropriate choice in a given setting for what kinds of technology or frameworks or systems to use. Any questions or doubts about these scenarios? No? Okay, so the final exam. So we don't have a final exam before you get nervous and have a heart attack. We can, however, try the following system to see how we get on, which is called Pokemon or Big Data. So you can test your big data knowledge. I have to stop and I'll have to share my browser. Okay. So what do we think? Arbok, is it big data or Pokemon? Pokemon? Very good. Akiban. I'll go with the first answer in chat. We'll see how we get on. Big data. Okay. Is this by negation? I presume this is because you know all the Pokemon and you're just negating, just applying a negation. Seahorse. Big data. Okay. Horsey. Pokemon. Very good. Hackathon. Pokemon. Oh, I don't know if that was for the last one or not, so I'll just go with big data. Big data. So lock-free architecture. I've never heard of hackathon except for in the context of this application. Lock-free architecture for SQL Server 2014. Not to be confused with Magneton. Okay. Ambari. Data. Okay. Ambari is big data. Again, I've never heard of it outside of this. Ambari is a tool that makes administration of Hadoop easy so you can make fun of the developers when they run out of executors. Not to be confused with Ambipom, which is the long tail Pokemon. Okay. Atlassian. Yep. Jira, effectively. Okay, I don't know if it's so much big data, but anyways, it's not Pokemon, so. Impala. Big data, there's some doubts in the chat on this one. It's a tough one. It's big data. So it's sort of an aggregation based database for running sort of aggregate queries efficiently. Vulpix. Pokemon. Okay. Divisium. I don't know the answer to this one. Maybe big data? It's big data, a tool for turning your coherent relational data into indecipherable big data. I've never heard of Divisium, but also it's worth mentioning that this test has been around for like 10 years. So some of these systems here may be a little bit outdated. Gorbis. I couldn't imagine someone calling their NoSQL system or whatever Gorbis. It's not a particularly appropriate name. Okay, Flink. Big data. Yep. So it's a streaming platform for batch and stream processing. The logo is cute enough to become a Pokemon. It's true, the logo does look like a Pokemon, maybe a little bit too cute. Azkaban. Harry Potter. No Harry Potter, but I guess we could inspect here and see. Harry Potter. Okay. Correct. It even says it here. It's not related with Harry Potter. Okay. Adabas. I think we're nearly there. Big data. Oh, there's some debate. Big data or 9th gen big data. So, okay. Geodude. It's big data, right? Pokemon. Big Pokemon. Delibird? I don't remember how many there are of these Pokemon. Okay. 25th of December is his favorite day. Why is that? So it's like Santa Claus. Arvados. Ah, this is red and white. Santa Claus colors. Any idea? Big data? Okay. Spins a web of microservices around unsuspecting sysadmins. Hadoop? Yeah, I think we got it. Never heard of it. I'm very disappointed. It's F in the course. Distributed system for counting words. Okay. Azuril? Cute Pokemon. Oh, it is a cute Pokemon. Okay. Geode? Big data. Yeah, it sounds like a trap, right? It sounds like Geodude. Database-like model. Not to be confused with Geodude. Pangool. How many of these are there? We're running out of time for the class. Big data. You'll break the system, Alonso. Nobody will be able to play if you do that. This game anymore. Divas. Pokemon. Spoink. Pokemon 2. Splunk. Yeah, I was actually going to make that mistake. Okay, so it's a good thing. Jirachi. Pokemon. Titan. I know this one. This one's a graph database. Distributed graph database. Hummingbird. Sounds like a Pokemon. It's big data though. Yeah. Twitter technology. Toku Tech. I have no idea. Big data. Hooray! 100%. I think this is the first year we got 100%, but usually I think it depends more on Pokemon knowledge than and the negation of Pokemon than that has to do with big data knowledge. I don't think anyone knows all of these big data systems. Okay, so share screen. Well, there's nothing left, I guess, anyways, but. So that's the final exam. Congratulations on 100%. That's the end of the course. I hope you found it useful. In terms of the content, the classes of the course, this is the last class. We still have the projects to come, of course. So on Wednesday, we're going to dedicate the time to, we'll be around to do Q&A for projects in case you have any doubts or questions about the projects, about the preparations of the talks and so forth. So all the sessions from now on will be opportunities to ask questions about the projects. I'm also, we can probably reset the Discord so that we can set the groups to a larger size, or maybe we can leave the groups closed and just try to set the max size to 4 so you can form groups with your project. And that would be it. Any questions or doubts?
Yeah, I have a question.
Sure.
About HDFS. I have seen that we have used this a lot in a lot of labs.
Yep.
Not just for Hadoop. So I was wondering, this can work almost in every distributed system.
Yeah. So
it doesn't matter the another technology we use. It is like almost always compatible with every technology.
To a certain extent, because it was the first sort of widely deployed open source distributed file system that's still heavily in use today, the systems that came afterward implemented support for HDFS because it was a very common thing to have your data on HDFS. So or they used HDFS directly as well if they're working with the disk. So it's very common to have support for HDFS storage in all of these systems. HDFS in general is sort of grouped together with Hadoop a lot. So when we saw those analyses earlier of the keywords, Hadoop also includes the HDFS, Hadoop distributed file system component. Yeah, so HDFS is quite common, used for persistent storage and distributed file systems in terms of just files, raw data. Yeah.
Okay, so HDFS, it's more like I don't know how it's said, like a protocol. It is a technology which has to use HDFS.
And I mean, you can use HDFS directly as well. Like you can store your files on there. You can, delete files, remove files. But that's all it provides you is this file management system. So a file system distributed over multiple machines. So the interface is very low level. So then, but it's like on your notebook, your PC, your Mac. That part of your operating system or the things associated with the file system. And then on top of that, you have lots of different applications that can access the data on the disk through the file system. It's a very similar analogy, but in a distributed setting.
Oh, fine. If I would like to have HDFS on my server or a lot of servers, a lot of computers, I would need to install HDFS in every computer which is using HDFS, and they would need to have some sort of connection, maybe Ethernet or some kind of LAN connection.
Yeah, exactly. Yeah, so typically a local LAN connection, and you would also need to configure a master, effectively a machine that's in charge of coordinating the HDFS cluster. So you would need a name node and maybe a backup as well, a secondary name node for that. And there you would assign essentially the information about which machines, where they're located, how they can be connected to. And also maybe high-level configurations about where, for example, each machine will store the data for HDFS on the local file system. So, the HDFS data is still stored on the local file systems of each machine on the hard drive. These sorts of configurations would need to be set, but yeah.
Fine, thank you. And how does it happen when we are working with Google or Twitter, when you have like a lot of servers or data centers distributed all over the world? So how could I communicate a data center in Brazil and in the United States and in Europe at the same time?
Yep. So you would typically only do that if you had a very high demand for very high availability. So this would be, in most scenarios, you'll be working within one region, one sort of server region, which will be within a local setting. So if you want to be able to communicate across different regions, that has a cost. So, you could be trying to maybe replicate or mirror services across multiple regions. That would be quite a rare scenario, I would say, because these cloud services in general, of course, provide very high availability. But if you wanted to do that, there would definitely be a cost associated with that. However, you could, for example, have you could have replication in two regions that are geographically close by, which can help. So in the East Coast of the US, for example, or two regions in the US or in whichever other country. And that might help to defray the transport costs. But I think the transport costs, it's not just a question of time and bandwidth, but also of economy at that point. So if you end up having to transfer lots of data between regions, it can become very expensive, I believe. So it's possible to organize all of that, but typically, unless you have a very risk-averse sort of scenario where you don't want anything bad to ever happen, you're probably gonna, especially if another scenario is that your application is quite simple. It doesn't have a whole lot of resources required and it doesn't change all that often. Then you can put them in lots of servers because there's very little coordination between the regions. But coordinating lots of data between regions can be costly.
Oh, fine.
Yep.
Yeah, thank you.
Okay. More questions or comments?
Oh yeah, sorry, another question. I don't remember the name of the technology we used to do the steps, like implementing a chat server,
The
like
RMI.
Telegram.
Yep, the RMI, remote messaging interface.
Yeah. So could we implement some API using RMI?
Yep, for sure. When I was working on my PhD, I built a sort of a MapReduce clone in RMI. So yeah, you could use RMI from the ground up. RMI can be a little bit tricky to manage in terms of some networking details and so forth, but once you have it working, it's quite it would be a good way to build a distributed system from the ground up in Java. I don't think that HDFS, Hadoop, and these Java-based distributed systems are using RMI. I'm not sure why or why not, but you could build a distributed system directly based on RMI with whatever APIs you would like to have. But there's probably a built-in solution for what you want to do at this point. If your problem is not unique, there's a very good chance that there exists some sort of system somewhere. If you wanted to build messaging in a distributed system, probably you could use something like Kafka, for example, this sort of thing. Or, maybe you could use Zookeeper if you wanted to manage certain values. But, there's plenty of options out there for this sort of thing now. But if you wanted to build something custom from the ground up, RMI would be an option for sure.
Of course. Thank you.
Okay.
I was mainly asking because I saw that you can implement your own methods using stubs. So that was quite amazing that you can execute a function in another computer or in another server.
Yep.
Remotely.
And you'll find the same thing in many programming languages. If you don't like, it's this general implementation in Java of RPC or remote procedure call, which you can find in other programming languages as well. And it's quite nice if you wanted to build something from the ground up. It's something I used a lot for my PhD because I had to build distributed systems for certain things I couldn't process on one machine. And it's not that difficult once you understand the abstraction. It's really just like calling a method on another machine. So and Java, the RMI framework will take care of a lot of the details underneath. So, yep.
Yeah, fine. Thank you.
No worries. Yeah. Any other questions or?
Oh yeah, sorry. I was wondering, how would you install all of this? Because I saw that all the labs you were giving us, they had already the jar files and the Java source files, but how would we install all of that? Because, well, we are used to using maybe JavaScript and just, or maybe Python, which use pip or another repository with all the files and modules you need.
Yep.
So it's quite rare how you would use Java to implement all of that.
Yep. So in terms of installing, let's say you had some new machines, you have 4 or 5 machines and you want to install these elements on the machines. The first good news is that there's a lot of documentation available online. But the second thing would be, it depends on your operating system. For most of these sorts of systems, you're probably going to run Linux, you're probably going to run Debian or Ubuntu or some sort of Linux distribution. Then you would essentially just need to use the sort of apt-get install or whatever the equivalent, apt install, whatever the equivalent command is for your distribution of Linux to install the packages. There's then some configuration files that you'll need to edit to make sure that, all the machines can see each other and connect to each other. And that's pretty much it. The most difficult part of the installation, and it's something that we still play with in the cluster from now and again, is configuring exactly the settings of the cluster for things like the MapReduce, the Hadoop framework, in terms of how many things can run in parallel, how much memory each task can use, these sorts of configurations to make the most out of the machines without generating problems on the machines. This is the sort of difficult part. But the installation itself, okay, you need to know maybe a little bit of, you need to be familiar with sort of Unix and these sorts of commands. But that would be the general concept.
Okay, thank you.
Yeah. So the good news just in general about that is there's loads of documentation on how to do that. So if you want to install something, of course, if you go to a cloud provider, you can just ask for these things to be pre-installed on your cluster. So you can just launch a cluster with Hadoop, Spark, Kafka, whatever you want, right? So that's already taken care of. No worries for asking. Any other questions or comments? If not, see you on Wednesday. We'll have the session for projects. So, yep.